to the channel. My name's Matt Dickinson. I am going to go through something a little bit more extended today. If you remember last week, what we'd essentially done is we'd looked at some servos. Apologies. We'd looked at torque actually using Simmultibody. Simmultibody is a extremely powerful bit of kit, really good for exactly what I do. But one thing that we're really not done with overall last week was we'd not and taking this to the next level, which was doing something where we want to find out what in the hell something's good for. Is something going to be useful? So what I thought I would do is take us down the actual road of looking at curl, which is the open source free exoskeleton, the shoulder one. So let me bring this in. Let's have a little look around it first. So in curl itself, the principle of this is dead simple. Shoulder blade. This is typically made of TPU, and then it is connected. That needs changing. Just realised it is connected all the way down to the bicep, which then has a motor which drives a connecting arm through to the elbow section, as I like to call it, the elbow piece here, and then the forearm causes reaction. So what you end up with is the curling action. But the beauty is, because of the rod ends around here, it means you can swivel your arm. So you're not compromising someone's ability to move. Which in this line of work, designing exoskeletons or looking at the exoskeleton approach, it's incredibly important that we don't injure someone in our processes. So this one in particular, the one that you can see here, is a 25 kilo servo. Now, it used to bug me, what does 25 kilo centimeter servo mean? And you go, it is kind of confusing. So let's just take back. Now this is the exact one that is fitted to mine at the moment. And what you can see here is it is a normal servo. It is, they are from what Bangor good. It is 47.79. So it isn't a cheap bit of kit. However, as a bit of a servo goes, this is incredible. So what this actually refers to is this is a 25 kilogram centimeter. So this is centimeter from the center of the arm along the horn, and that's what it refers to. It refers to that 25 grams. 25 kilos from there. So there's a bit of a performance. This is actually quite a strong servo. Granted, you can get more. But yeah, as a piece of kit, it is quite a strong piece. I've just realised that's 6, so let's push it to 1. Oh, £10.35. It's a deal. It's a steal. But yeah, so that often you kind of sit there and go, is that going to function for what I want? What I'm going to do is I'm going to bring in my Matlab. So let's go to Matlab, wherever that may be. So I'm going to go into my Matlab. And I'm just gonna let that load. But first things first, I actually need I need a folder. So let's take this back. Now, as the overall piece itself, fab. Now let's get over to the actual arm itself. So I'm gonna go sub-level. So anybody who's managed to get hold of this model, you'll know that you can keep going into levels. I love levels. I love organization. I don't like all these bits and messing and things. And we got, right, here we go. So we're that little bit closer now. So I'm going to perhaps I'm just going to hide that for the moment. And this is our servo with horn. Okay, and we know it's going to be so I'm going to presume, in fact, let's just take a look about what actual distance that refers to. So I'm going to go measure from my center. This is going to tell me where to load it up, that's all. So I'm going to measure from my center. And I'm going to go to here. How far is that? That's 20 millimeters, 2 centimeters. I think, really, it's going to go... Realistically, I think we're looking at there. And something like... can I get... Oh my goodness, I can't seem to get this damn thing in the right spot. So, something like... come on. Oh, I can't get it. Okay, let's try it again. Oh, come over here. and then come on. There. 8 point. Yeah, so we can presume that's our distance. That's our 25 kilograms. So it's 25 kilograms centimeter. So it's that, and that kind of implies it. It's probably a little bit different, and it's probably a little bit over here. But yeah, that's my single centimeter there. Okay. So what I'm going to do then is start to export. I need these parts. So first things first, I'm going to open up my model. And there we go. That's the model itself. That's my my servo. So I'm just going to make myself a folder. Don't forget, when we're doing this, you need an operational folder. So I'm going to call this servo test. I just want to see how much this thing is going to do what I want it to. And put everything into that folder. Whoops, wrong button. So now let's just extend here, and then let's get back to it. So what I would like to do now is just export this as a single step file. So I'm going to go File, CAD format. And if you're a SolidWorks user, this will be slightly different. You can you just go to Save As, and you can jump in your own format. So I'll come here, and I don't want to export as like that. I want to actually bring it out as a step file. 3, 2, 1. There we go. Oh no. PCs are great when you don't have to wait. Right, there we go. So I want to bring out the servo. Click OK. Now, to aid me in my design and to aid me in my simulation or test, if you will, what I'm going to do is I'm actually going to leave the CAD file open because I'd like to just double check a few things. While that does its is that done? While that does its merry business, I'm just going to jump over to Matlab. Let's see where we are here. Now you see, the reason it's freezing up for me, there we go. Is that done? Oh, no, still ticking over. Okay, so, oh my goodness. Okay, so that's now exported, and we're now happy with that piece. But again, I'm going to leave that open for the moment. Now I'm going to go back to my servo assembly, and I want my horn. So I'm going to open this up too. So let's open that up, and take a quick little look around the geometry. Now the geometry is actually a little bit horrid, and it's just to do with, you see, this particular model was given by the company. And this is just an advertisement model. I've never produced this model myself. I do look at it and I keep thinking to myself, perhaps this is a well worth endeavor to ensure my accuracy of the things moving forward. A quick review confirms it is one single solid piece, which is good. So then what we'll do is drop that out. So I go to File, Export, into my CAD. Again, this is just for Inventor users. For me here, I'm just using for me, I'm using Inventor, but for those of you using SolidWorks, you'll do a Save As. So it's not too much of a difference, but we've got the servo here, and now I'm just going to go horn. Now, what we know is we want to just test and see what this servo does. Now, it's said on the guide that, if you look here, well, let's have a look. This is a 180-degree servo, big indicator. We now know it's motion, and I can feel a lot of people instantly saying, well, technically, a servo doesn't move 0 to 180. That's very true. It actually moves 1 to 2 degrees and minus by 1 to 178, something around that spot. But they are advertised, so we'll advertise. We will operate based on their advertisement, but we can modify that if need be. So let's come back onto the actual area. Now I'm here, and I'm still in my exoskeleton stuff. I actually want to move from here. I want to move to the folder that I've just set up. So I'm going to go browse. I'm going to come across to my desktop, click onto Servo, and then click time. And there we go. So I've got my servo and I've got my horn. We're all good. So what I'm now going to do is set up my Simulink model. Now we can move like we've got a purpose. The beauty is I think over 5 seconds, or maybe let's go, 5 seconds we can do 0, 180, 180 to 0. Then what we can do if we want to be nasty is let's load it up with that 25 kilos. Let's see how much this thing can actually perform. Because if you're like me, which I'm guessing a lot of you will be, you'll be kind of sitting there going, do I really trust everything I'm getting here? Is it true? Anytime you buy an engine, they say, oh yeah, we will get this level of efficiency. But this all comes from when the engine is placed on the dynamometer. So when it goes from the dynamometer to your production car, you get variational changes. So you don't exactly get that overall top performance. But for what we're interested in is when this is actually onto someone's arm and it moves, what's the experience going to be like? Or, I mean, you're never really going to know. You can't figure out the comfort and the approach of what you're doing. But when you're designing the exo, when you're thinking about your exo, the motor that you use will by default really change the overall experience of what people are getting when they actually wear the exo. Don't get me wrong, if you're talking special forces operatives, then fine. These people will be well trained, they will be well acute to their bodies, they will know what their bodies can do. And they have so much going on, they're probably not going to be too bothered if you've got something that feels strange to wear. They just want to know this is going to work and this is going to not hold them back in a very big job that they're doing. However, if we go right to the position of someone who's in rehabilitation, that position of comfort is incredibly important. It's incredibly important because unlike your special forces operatives, what you've got here is people that really don't have an awful lot of choice. The special forces, they can just take it off and go, you know what, I'm not wearing it, and still be able to commit to their task. However, if you have somebody who is in rehab, they are actually wearing this for rehabilitation, or in some cases to allow them to walk again for the rewalk exoskeleton. So there's so much going on when we refer to that. But what we're going to do here is we're going from Simulink. I'm going to set up a blank model, and then what we're going to do is we're going to see what our motor can do and inform us about that way moving forwards. Okay, so it's actually quite ironic. For the rambling I was just doing, or just talking, it just gave me enough time for the system to boot up. As a reminder to everybody who's following me through with this, first time you hit run, it takes a while because it's got to load Matlab, and then move to Simulink. Somebody asked me as well this week, where do you see this used? Crazy thing is, everywhere. One of the most impressive things I've ever seen is the work that was done by NASA when they were considering Curiosity coming into Mars. And this system was used to be able to predict the conditions of when it was coming in for flight. Super impressive and far more intelligent and like far more super people than I, but very impressive. And if you do get a chance, make sure you dig it out on YouTube. Great thing to watch. Okay. So from my MATLAB, again, it's so anticlimactic. You go, wow, blank page, brill. So what I'm going to do is go new apologies, library browser. If I'm talking funny, I've had a piece of my tongue just taken off this week, so it feels a little strange to talk sometimes. Okay. So what we've got now, we've got our overall space. If you remember from what we did on the last one, we need our baseline, we need our foundations. So I'm going to extend, and I'm going to go to solver configuration. Again, I want to tap into the brilliant physicists who've formulated and built some of the solvers that exist within the Simmultibody Matlab or Simulink system. We might want to change it, we might want to play around with it, but let's just stay with what we've got for the moment. Again, remember, it's going to take time for the first one. So then I'm going to go to multibody. I'm going to go to frames and transforms, and I'm going to go world. I'm going to really fairly move quickly here just because I've rabbited a little bit. And then I'll come down to utilities. And bring in mechanism configuration. So these are my 3 vital pieces. Again, if anybody's curious, this is my absolute go-to tool when I designed curl, when I designed the system that we're working on at the moment, which is an active muscle imitation, so it's a cable contraction method. Everything designed through here, and this is a great system for things like this. Pretty good, I should say, if you're looking to drive. If you're doing passive, I'd still lean more on to your FEA analysis. If you're looking for an active-based system, nothing better. And what I'd like to do over a couple of weeks is perhaps look at a shoulder one as well. In particular, the Ottobock shoulder, or at least a loose design like the Ottobock, and then let's see if we can simulate that too. So, with the same theory, what I'm going to do is just bounce back to my model. We've got the servo, right? So what we need to be able to do is we need to be able to place the horn in position so it will rotate around. Let me just turn that sketch off, by the way. So it will rotate around. The horn, again, as we know, what it actually does is it places interference over the top, and then you put grub screws into it, which compress it and actually grip onto the top of it. I know I've built so many of curls at the moment that I know exactly how this fits. So what I'm going to do is I'm just going to let's have a look. I'm just going to look at how this has really been applied, and you see there it's actually sitting just above, which is how you will find it on NA. So what I'll do then first is we need to bring it in. We know if we're going to test this performance, this will sit in situ, and this will just rotate an our 0 to 180. Again, which we can edit if we want to. So I'll come back onto here. This time I'm not going into the joint first. I'm actually going to go into the body, and I'm going to bring the body in first. So let's go. Dangerously, I've actually not practiced this, so if something goes wrong, this will be a true things going wrong. So first, let's just click onto here, and I'm just going to call this. Let's call this servo body. I can call this anything I want. It just depends. So let's go servo body. You could rename it whatever you want, but for me, that's going to work. What we're going to do is we need to now really examine exactly what it is that we've got. So I'm going to just browse. I'm going to come across, go to my servo, because you'll see here I'm straight in here. The hard thing is the weight. We often need to make an assumption. I don't like making an assumption, so we'll try and do the homework that we can. So that's the servo. So let's bring that in. That's the servo, and as you can see there, it's typical. So The weight of this servo actually is suggested to be, overall it is 67 grams. So if overall is 67 grams, let's see if this is made of aluminium, how much this thing weighs. Because I'm presuming this is with horn. It might not be, but I'm presuming it to be with horn. So this is made of aluminium. Let's do a tools. Let's do a measure. This is just face. I don't want face. I'll come back to this. So what I'll presume then is I'll go onto here. I'm gonna go onto here, and I'm gonna just bring this in for the moment, and I'm gonna assume this to be. Let's go. Tentative from file. Is that going to do it? Nope, not going to give me anything. Okay, so let's just do density. Sorry, I'm going to do custom mass. And 67 grams. Not much. Amazing, really. So from 67 grams, we calculate this. And of course, it just gives it an overall. And we're going to confirm that. Now, I'm not really too fussed about that in itself. It's not really the weight I'm bothered about. It's more the performance I'm looking for. So I'm going to bring in my triad. Triad's not so bad. Good spot for starting. This looks pretty good. This looks promising. Okay. So I'm going to click apply and then close. Where this is connected, I'm going to connect it here. Whoops. I'm actually going to connect it here. Bring that across like that. Now, from this servo, what we know is it rotates. We know it rotates around the top, that plus or minus 180. So then what I will do is I'll bring this back and go to joints. And then I'm going to go to revolute. Bring my revolute across. And I'm going to snap this in. Good thing is with what we're doing here, you could easily look at alternates. This servo might not be any good for your application. If you want this to perform highly, much better, we can find out from this. Because we can put in the maximum performance of this servo and see what happens. Apologies, I just had a quick update. Right, so what I'll now do is I'm now going to go again. I now need to bring in the horn. So let's go file solid. Because my revolute's here. That's my base. So this is attached to the base of the servo. Then the rotational axis, which is this behavior, and then the follower in this case to be the horn. So I'll call this, I never know, you know, why they actually call it a horn, but they call it a servo horn. Okay, so then we attach it on, and I'm just going to bring this back, and I'm going to go here, and I'm going to go to horn. And then let's go F5. This is where it becomes a little bit annoying, because if we look now, there's some of the surfaces on here that are a little bit damaged. It's okay. We're going to assign. We're going to manually assign a density, so it will still do its job. So I'm going to go mass. I mean kilos. Yeah. Okay. Then we'll go grams. I imagine that this is something like 7, 8, maybe 10. Go 10 grams. I'm just adding that on. So I've got 10 grams on here, and I can change the density, of course, but I've got 10 grams, And what I'd also like to do is I'm going to change the color so I can clearly see the differences of what's going on. So click OK, and then let's do an F5, F5. So there we go. So now we've got, now this is what we also need to do. We need to look at the triad. So, oh no, look at the triad. Triad sits at the top here. This is not good news. Actually, what we need to do is we need another triad that's going to be operating around the edge here. Just because where our triad sits on the servo is bang at the top, and we know that this lower edge is where the servo interfaces. So let's do apply, and we're going to have to go to frames. Now this frames function here is fab. It allows us to do some crazy good stuff. So I'm going to go add. I'm going to come to my lower edge here and click there. Now you see that arrow? That arrow just confirms the vector in which way it's moving. What I'd like to do though is assign this. So let's call this horn connect or horn C. It's just an easy one. I'm going to go where my frame origin is. I'm going to go based on geometric features. So click there and then click select. Now what you see is we've got an extra one that's been applied. This one is more accurate to what we need. So what I'll do is click save. And now we have two. Now you see there we've got two, but you'll also see here it says show port R. R is now irrelevant. So what we're going to do is we're going to drop that off and click apply. And finally, if you remember, we were guessing at the idea of that our 25 kilograms is going to sit here. So what I'm going to do is I'm going to attach another marker to this edge. So this can be my test point. So like there. And I'm going to call this test point. Test P. And we'll go based on geometry and then apply. So now don't forget, in our system, they're all based on, all axes are based on Z, but we're gonna place a force on this, or and we're gonna look at what it can do in its operation. So I'm gonna click save, and then what I'll do here as well is I'm gonna do one last piece and stick it on the end, because that's really what I'm gonna use. I'm not using any of the others. So I'll stick it on the end here, and I'm going to go application. So really I can verify, make sure it works like I want it to, and then see what it can do. So I'll go place and then select. And again, Z sits in its default, and then I'll go save and apply, and then OK. We are now got an awful lot of things going on. Now you've got to remember what the names were for things. So let's have a look. We've got test piece. So this is where the servo is actually connected. We have application, where we're actually going to be applying this, and we've got home horn C. That is where that actually sits. So that tells me that we're now connected. So before I do anything, let's just hit run. Once you run this piece, what we should just get is a rendered version of the system in space. Now, what's an important thing to realize here is when this renders up, it looks like we want it. So that's looking good. That's looking very positive. Very, very positive. This is great. We sit here. Now it's not doing anything just because it's 0. If you remember, we've actually got nothing going on here. And there's no reason for it to move yet. But it will do in a minute. So the next thing, what I'd like to do now is, there's a few things really. I'd like to, I'm going to put force on this. I'm going to wreck this thing like mad. But I want to see what's going to happen. So I'm going to just double click into Revolute. I'm going to apply. I'm going to go. I don't want to apply a torque. I'm going to have that automatically computed. I'm going to apply a motion. I'm going to go input. Now this is different. This is so different because now what I'm doing is I'm driving that 0 to 180 position. Now if you remember last week, you can just type this. So I'm going to go sim. Sim to power stream converter. 3, 2, 1. Bring it to there like that. What do I want this to be in? Of course, I want this to be in degrees. And input handling. We're going to come back to this. We're going to find out what's happening because this isn't going to work. Other thing that I want is a signal builder. So I'm going to go signal editor. Now the signal editor is a new system. The signal editor replaces what was the conventional signal builder for anybody who is a Matlab user. It is great piece. It does an awful lot, but in this one now we actually model. We model the system. So in here where it says create edit scenario launch signal, what I'm going to do here is I've clicked on it, and what it's going to do is it will load me up this. You kind of go, oh, what's that? This is where I can actually draw the signal I want to work. It wasn't always like this. It wasn't this good. It was kind of like you had to fiddle around, get it all working, and it was a mess. So I think over 10 seconds, let's go from 0 to 180, and so let's go. So we're going to go 0, and then what I'm going to do is I'm going to add. I'm going to get to 5. When I get to 5, when I get to 5 seconds, I'm going to be moved to 180, and then what I'm going to do is after that I'm going to come back. So let's just zoom that out. To go over that 5 seconds, move to position, and then come back. And that's all it'll do. But don't forget, this is just simply a value that's been drawn here. I can add, I can design, I can put curves into here if I wish. But as a first starter to understanding the signal editor, this is a great tool. Now what's cool with this is if I simply go to editor, and then I go, you know what, I'm happy now. It'll say, do you want to save? I do want to save. Now this is something it didn't always do. It used to just go, right, cool, well done. You know, here's a gold star. Now it actually converts what I've just done into XY data so it can read it. And you can put this into other things if you need to plot the signal that you're working with. So let's call this servo out. I've just got servo out. It just gives an idea of this thing moving from one to the other. And we'll click save. And again, I could easily change these to be higher and lower. See there, servo out.mat is loaded, and scenario, signal type, units to be brought in. It's coming in inherent in this case, but that's fine because in our converter, we've already set the units. Click apply, and then OK. Now, let's try running it and see what happens. You kind of look and go, but what happened? Okay, this is what annoys me. This is one of the things that annoys. It's always annoyed me, but it is important. It kind of comes here and goes, what you're doing doesn't really make sense. This is because you're trying to put a value in there, and there is position, velocity, acceleration, and that needs to be ticked off. There needs to be a reason to have all these key things there. So what we're going to do in our converter is we've got to consider the output filter. How is this system going to behave? Is it an input with first derivatives? If it is it an input with two derivatives? Is it a filter for first order filters or a second order filter? So second order filter, what does that mean? A second order filter would imply that the system moves with an overshoot. You kind of go, but a DC motor, when it drives the system, it'll come and you'll get a slight overshoot. Don't get me wrong, we may not see this, but you might get that overshoot. Also, I've got a time constant here. And you go, this could be more like what I'm after. Okay, so let's just drop that out and take a look. And you go, oh, hang on a second, or so it's looking a bit more like what we're after, but what's happening? It just goes 0, 0, 0, 0, and then snaps. And you go, that is not what we're after. So let's snap this back again. So what we do here is you come back and you look and you go, well, it may not be. Is it first order? But then you look and it says no. And that's because it can't be first order. It has to be. Okay, so let's go signals inputs, and then let's go by two derivatives. Oh, no, apologies. Then let's go to the zero derivatives in this case for piecewise. So this is just a direct driving piece. And you go, yeah, none of these are working. When really, it is actually our second order system. And what it's actually not happy with is it's coming in degrees and units. And let's have a look. So the system comes across and it's coming onto here. And let's take a look at what it's actually seeing. Degrees, apply. Let's just see, have a look. So it's still snapping. Okay, sorry everyone, I was just having a little bit of a play around to figure out what was not quite working for me then. Now if you're running it, and I didn't realise this, I just paused the recording for just 2 moments, just so I could figure out why this was playing very, very strange. And it's not playing strange, it's got a new function. So cool. So if I hit run, you kind of go, what's going on? I've just told it to go 0 to... What? Now, conventionally on the signal builder originally, you didn't have an option of looking at a step. You just had to do as it was told. But I just realised there is an interpolate of data. So if I interpolate my data, which is to interpolate, it will give me an overall, and then click apply and OK, and we run. Now we've got what we're after. Look at the smooth output. We go 0 to 180, and we go over that 10 seconds. So we're now getting what we get, right? So this is now moving perfectly. This is just what we want. And what we know is if I hang 25 grams here for our test position, if I hang 25 grams, I should get the output of Newton meters of this motor. So what I'm going to do is go sensing. I'm going to go actuator torque. So let's go actuator torque. In fact, no. Let's go composite, and I'm going to go all the way. Let's go total torque. This is everything that's in the system at the time. It'll still give us roughly the same, but at least then we'll get everything there. I'm going to bring that up. Pop you out of the way a little bit. Let's extend that up. And what I want to do now is go power stream to Simulink converter. So I'm going from one way to the other now. Bring out there. And then I'm going to go scope. And there we go. So now, if I go, and what we're going to get now in here for a total torque, obviously this is going to come out as an inherent. I'd like it to actually come out in Newton meter, because this is just going to give me the torque. So if I run it, now what we get again is, oh, hang on a second, what we're going to get. Come on. Here it comes. Any minute now. There we go. We've now got a Newton meter coming out of our actual motor. We've got total here, but it's really here that I'm interested in, my big blue line. And what you've got is spikes of operation. So what I'm going to do now, because we've got all that going on, is let's start to do some really cool stuff. So I'm going to go to my library now. I'm going to go all the way down to my torque, to my sim multibody. Go forces and transforms, and what you'll see here is external force and torque. So I'm going to go external force and torque, and I'm actually going to add this to my test piece. So put it over here, and now it wants to know, okay, what do you want to add? I actually want to add force, so we're going to hang it off the side. So I'm going to go Y. If we just, and then you notice there, tab came straight in. So this is cool. I really like this. So now let's go Simulink, sim, power string converter. What I'll do is I'm just gonna go kilos. It's gonna let me go kilos. It might not do, just because I am pushing my luck now. Oh, look at that. So I'm gonna go kilos. Then I'm gonna add a constant. This constant in this case is gonna be 25. We're gonna apply it now, okay. And then let's run it. Let's see what happens. Oh. It really wants to be newtons. So we're going for 250 newtons. Roughly. Now we run. Now let's check it. So you see, now we put it on the Y. So what this actually says is that it's hanging this way. It's hanging this way downwards. Now let's bring it back to the motor. Look at that. Look at that. So now what we've got is our overall. We're looking at roughly. Let's get you a measurement, shall we? What are we at there? 2.25. So that's 2.25 2.25 Newton meters of torque generated by the actual motor. Interesting. 2.25 Newton meters. This is fab. This is really, really good. So we now know that this will do an awful lot. Let's drop you off. I'm going to right click, comment that out, and now what I'm going to do is I'm going to see what will happen if I hang. Let's get an average weight of a human arm. Okay, so it's not the most accurate in the world, but the average weight of a human arm, about 150 pounds. Let's go forearm. It's just roughly 14.2 kilos. 14.2. So we're going to 142. So what I'll do, I can't be bothered. Right click, copy. Look at that. It almost feels like cheating, doesn't it? So I'm going to come on here and I'm going to come back, get over there, and let's spin that round. Oops. Spin that round. Bring that across here. And we were saying what? We're going 142. Roughly. Granted, you might want to change this a little bit, but it gives us a bit of an estimate. So let's run it again. So look how you are. Look at that. As an output for our overall flow of the torque. Well within our operational remit. For a forearm, this would do a great job. This would be quite good to aid it So this lets us know that if somebody was weak and they went to raise their arm, this would offer a little bit of support. This tells us that under the ideal conditions, this servo will operate incredibly well. However, my concern would be energy draw. This will probably run quite a bit of energy. As just as an estimate, I suspect that this will run quite a bit. But this is a great motor. Whoever selected this knew what they were doing. Do make sure, if you've not done, make sure you save this. This is a fab little example. But this is the servo that you actually find in Curl. So Curl, if anybody doesn't know, Curl is the free open source exoskeleton which myself and a few others have designed and developed. This is a great test rig to either learn about exoskeletons, how they function, or even test it for new control systems. I myself have a new patency under review for a control system, and I've used Curl. Curl actually sits in my lab, and Curl is a great piece of equipment for people to learn from. I also have students who develop Curl, so each year I'm aiming to try and introduce a new iteration of Curl for new free downloads. Other than that, my name's Dr. Matt Dickinson. I hope you found this somewhat as a benefit. This has been purely becoming more focused on which is my personal excitement, which is exoskeletons. If there is any burning questions, do put a line underneath and ask me, and I am more than happy to help. Other than that, I hope you have a great day, and I will see you all in a week.